have an example. Find the time taken by light to travel through a medium of width 500 meter having refractive index 1.3. Solution: velocity of light in the given media equals c by mu, which equals 3 into 10 to the power 8 divided by 1.3, which equals 2.3076 into 10 to the power 8 meters per second. We know that time taken equals distance by velocity. This implies time taken equals 500 divided by 2.3076 into 10 to the power 8, which implies time taken equals 2.166 into 10 to the power minus 6 seconds. Let us have another example. Light from a point source in air falls on a spherical glass surface of refractive index 1.5 and radius of curvature 20 centimeters. The distance of the light source from the glass surface is 100 centimeter. At what position the image is formed? Let us have the solution. We have u is equal to minus 100 centimeters and r is equal to 20 centimeters. We have n1 is equal to 1 and n2 is equal to 1.5. We know that n2 by v plus n1 by u equals n2 minus n1 by r. Therefore, 1.5 by v plus 1 by 100 equals 0.5 divided by 20. Thus, the image formed at a distance of 100 centimeter from the glass surface in the direction of incident light, or v is equal to 100 centimeters. Let us have another example. A small bulb is placed at the bottom of a tank containing water to a depth of 80 centimeters. What is the area of the surface of water through which light from the bulb can emerge out? Given refractive index of water is 1.33. Let us have the solution. Actual depth of the bulb in water equals 80 centimeter, which equals 0.8, and refractive index of water equals 1.33. The given situation is shown in the following figure. We have R is equal to AC by 2, which equals AO, which is also equal to OB. Here, I is the angle of incidence and R is the angle of refraction, which equals 90 degree. Since the bulb is a point source, the emergent light can be considered as a circle of radius, OC. Using Snell's law, we can write the relation for the refractive index of water as mu is equal to sin R by sin I. This implies 1.33 equals sin 90 degree divided by sin I. Therefore, the angle of incidence equals 48.75 degree. Using the given figure, we have the relation tan I equals OC by OB, which equals R by D1. Therefore, R equals tan of 48.75 degree into 0.8, which equals 0.91 meters, which equals 2.61 meters square. Hence, the area of the surface of water through which the light from the bulb can emerge is approximately 2.61 meters square. Let us have an example over total internal reflection. First part, given figure shows a cross section of light pipe made of a glass fiber of refractive index 1.68. The outer covering of the pipe is made of a material of refractive index 1.44. What is the range of the angles of the incident rays with the axis of the pipe for which total reflections inside the pipe take place as shown in the figure? Second part, what is the answer if there is no outer covering of the pipe? Let us have the solution. Refractive index of the glass fiber is given to be 1.68 and of the outer covering of the pipe is given to be 1.44. We take the angle of incidence as I, angle of refraction as R, and angle of incidence at the interface equals I prime. Also, the refractive index mu of the inner core outer core interface is given as mu1 is equal to 1.68. Mu equals mu2 by mu1, which equals 1 by sin I prime. Sin I prime is therefore is equal to mu1 by mu2. This implies sin I prime equals 0.8571. Therefore, I prime equals 59 degree. For the critical angle, total internal reflection takes place only when I is greater than 59 degree. Maximum angle of reflection. Let I max be the maximum angle of incidence. The refractive index at the air glass interface is mu1. We have the relation for the maximum angles of incidence and reflection as mu1 is equal to sin I max divided by sin R max. Sin I max equals mu1 sin R max, which equals 1.68 into sin of 31 degree, which equals 0.8652. Therefore, I maximum equals sin inverse 0.8652, which is approximately equal to 60 degree. Thus, all the rays incident at angles lying in the range 0 to 60 degree will not suffer total internal reflection. If the outer covering of the pipe is not present, then refractive index of the outer pipe is mu1, which equals 1. For the angle of incidence I is equal to 90 degree, we can write Snell's law at the air pipe interface as sin I by sin R equals mu2, which equals 1.68. Therefore, sin R equals 1 by 1.68. This implies R equals 36.5 degrees. Therefore, I prime is equal to 90 degree minus 36.5 degree, which equals 53.5 degree. Since I prime is greater than R, all incident rays will suffer total internal reflection.